Let's record. Okay, so let's start with number one. So number one is let A1, AN be a sequence of distinct positive integers. Show that the sum from k equals 1 to n of ak over k squared is greater than or equal to sum from k equals 1 to n of 1 over k. So this one is one where if you know the idea, it's pretty straightforward. So what's the idea?
Um, the lowest um lowest left-hand side is when you have A1 equals 1, A2 equals 2, and so on.
Right, so the idea is that the left-hand side
Or
is minimized. Yes,
minimized when AK equals K.
that's right, when ak equals k. So how do we prove this? There's one,
Um, we can use the arrangement inequality.
that's right, so we should use the rearrangement inequality. Right, so this is a very important inequality. So what does it say? It says that if 0 less than a, no, it doesn't actually have to be, actually it works even when the numbers are not positive. So if a1 less than or equal to a2 less than or equal to all the way to less than or equal to an, and b1 less than or equal to b2 all the way less than or equal to bn, then for any permutation, sigma 1, sigma n of 1 n, it's true that if I do the sum of ai times b sigma I, so I multiply the a and the b sequence term-wise, but I permute this one of them. So the maximum it can be is if they're ordered. So it'll be at most a1, let's write it like this. It'll be at most sum I equals 1 to n of ai times sum I equals 1 to n of bi. Sorry, that's not right. ai times bi. And the smallest it can be is sum I equals 1 to n of ai times b n plus 1 minus I. So this is the reverse if they're ordered opposite to each other. Yeah. So this is the rearrangement inequality, and yeah, so it applies here. In particular, it says that the left-hand side should be greater than or equal to. So let's at least let's rewrite this as ak times 1 over k squared. So 1 over k squared is decreasing. So if we want to make it as small as possible, we should say we should order them increasingly, right? So does it make sense what I wrote? I just AI prime is the sequence, or AK prime is the sequence AK but ordered. Okay. And then certainly this one is greater than or equal to the right-hand side. So does it make sense? By the okay, maybe to make it abundantly clear, we write it like this. We write this as k times 1 over k squared. Right? Yeah, so this is a straightforward application of the rearrangement inequality. Um, okay, so let's go to the second one. So number 2 is let x1, x 2023 be pairwise different real numbers, positive reals, such that a sub n equal to square root of x1 plus xn as 1 over x1 plus 1 over xn is an integer. This quantity is an integer for all n. So for n is 1 to 23, prove and a 2023 is at least 3034. Okay. So how do we go about solving this one? What are some first observations or ideas or something?
Um, if the sequence is increasing, so
Yeah,
it
so
should increase by at least one over time.
right, so first, I guess it's increasing.
And if one equals one.
Yeah, okay, so maybe what are the observations? So first let's notice a sub 1 equals 1 and an is increasing. Good. So moreover, the fact that they're all integers, all this, okay, this at least gives you a 2023 is at least 2023. But we need better, so maybe what can we do?
Um, I solved it by proving that um, the sequence can't increase by exactly one twice in a row.
Right, so yeah, so what's the main idea? So this is the key idea. So we know the sequence is increasing, and because it has integer values, it must increase by at least one, but it cannot do that twice. So maybe let's say it like this: there does not exist. Sorry, that's not what that means. There does not exist k such that ak plus 1 equals ak plus 1 and ak plus 2 equals ak plus 1 plus 1. Yeah, so it cannot increase by one twice in a row. And then okay, you have to think a little bit carefully, but then it'll follow. So how do we do this?
Um, uh, you just you just assume, or you can just write the nth term or as um, uh, r squared divided by s times s, um, and then you add x n plus 1 and 1 divided by x plus 1 to uh, anyway, you add another term and suppose that it only adds 1 to a of n, and then you solve the equation, and then you try to solve it for a of uh, n plus 2 and see if
Mm-hmm.
you can add 1 again, and it gives you and the solving the equation gives you the same solution. And since the numbers have to be distinct, this cannot happen.
Yeah, so you're saying that if I say, so first you're saying I should write AK plus 1 equals AK plus 1, and you're telling me that this allows me to write xn in terms of the other ones. Is that the idea?
Yeah, but you can write as square root of um, or you can, yeah, square root of and open brackets s squared divided by r uh, plus um, x k plus 1 close the brackets, and then r plus 1 divided by x plus x of k plus 1. No,
I understand. Yeah, no, I understand. So r plus xk plus 1 over xk plus 1 like this.
yeah, and then you solve the equation.
I see. And you're saying what are s and r?
S is S is a of k.
Okay. Uh, so maybe I'll just write AK or something.
Yeah,
And what is r?
um, any number such that a k squared divided by r gives you x1 plus x2 plus until x k.
Um,
Um, and so r equals
I understand now what you're
yeah.
saying. Yeah. So what you're saying is whatever number I put here and here, so these two numbers will multiply to AK squared, so I can write it like this. I understand. Okay. Very good. Um, and so okay, maybe we'll just write explicitly r is basically equal to I guess 1 over x1 plus 1 over xk, right? Um, okay, and then you're saying if I take this expression, um, maybe I'll move this to here. And so this is equal to, and yes, what do I do from here? I want to say this is equal to AK plus 1, and you're saying that will give me um, an expression for xk plus 1. So, uh, sorry, I want to write AK plus 1. Okay, so, um, okay, and then what does that mean? So it gives us AK squared plus rxk plus 1 plus um, AK squared over r times 1 over xk plus 1 equals ak squared plus 2ak plus 1. And I see. And then you're saying this is true. Um, okay. So is this what you got as well? Kareem, is this what you were suggesting? Something like this?
Um, yeah, and then you calculate x k plus 1 in terms of ak and r,
Uh-huh.
and then you try to do the same for ak plus 2 and find that xk plus 1 equals xk plus 2.
I see. Okay. Yeah, so maybe there's a lot of calculation, but let me just make some comments to sort of yeah, so let's just make some comments. Um, yeah, I guess the point here is um, so what's going on here? This left-hand side, you can basically you can bound it by AMGM, and what's true is that yeah, if you there's actually this is just there's an inequality here um, because the product of the two terms here, this one and this one, is actually AK squared. So by AMGM you get yeah, so this is AMGM.
Um, I don't get why this is necessary.
I'm
Since
not.
we supposed that it was plus 1, so it must be equality and not greater than or equal.
So yeah, it's not necessary. I'm just sort of maybe explaining what's. I mean, then you have to sort of say, okay, how do you know? Like when you have this equation here, how do you solve for xk plus 1? The point is, what happens is okay. Maybe I need to create. I need a little more space to explain this. So um, okay, let me erase what's here. So the point is, okay, you have this. Um, um, and then when you try to solve for xk plus 1, the way you do it is I think at least what you should do is you should say um, okay, r xk plus 1 squared minus 2ak times xk plus ak squared over r is equal to 0, which becomes um, square root of r xk plus 1 minus ak over square root of r squared equals 0. And so xk plus 1 equals ak over r. Um, so there's something special which is happening, which is this expression is a perfect square. And the reason for that is because there's an inequality here, and that's the equality case. Does it make sense what I'm saying?
Yeah,
Right.
now,
So it's not necessary to do this inequality business, but that's sort of the point here is that um, there is an inequality by AMGM, and the equality happens when the two things are equal. And so if you set this one equal to this one, then you'll find xk plus 1, you'll find this. Xk plus 1 equals ak over r. Um, So it's maybe some kind of minor observation, but maybe it explains what's happening a little bit. Um, um, and maybe yeah, so maybe I'll um yeah. Okay, so basically yeah, the idea is, um yeah, so you'll get this, and then when you solve for uh when you add this as well, what you'll find is that xk equals xk plus 1, or xk plus 1 and xk plus 2 are equal, and that's a contradiction. Yeah, so let's just write that down. So what's the idea? What you'll find is that this is equivalent to, maybe this is the key lemma. Um, um, so this is a lemma now, that ak plus 1 equals ak plus 1 if and only if xk plus 1 is equal to ak over r, where r is equal to 1 over x1 all the way to 1 over xk. Okay, and then you can show, so then maybe lemma 2, uh, if uh, ak plus 1 equals ak plus 1 and ak plus 2 equals ak plus 1, then xk plus 1 equals xk plus 2. Um, and that's some kind of straightforward calculation. Um, yeah. Okay, so any questions about this one?
No, nothing.
Yeah, okay. Um, okay, great. So let's look at number 3 now. Yeah, okay, so any ideas for number 3? So let me write the problem. So you have a sequence A0, A1, AN defined by A0 is 1/2, and okay, let's first write it like this. A0 is 1/2, and AK equals AK minus 1 plus AK minus 1 squared over N for K between 1 and N. And what you want to do is prove um, that AN is between 1 minus 1 over N is less than AN, which is less than 1. Yeah, so you have some sequence and you want to bound the last term, basically. I guess it's a pretty tight bound as well. So any ideas where we can start? maybe we can write out a few examples. For n equals 1, the sequence goes a0 equals a half, and then a1 is equal to um, maybe 3/4, right? 1/2 plus 1/2 squared. Yeah, so that's 3/4. And then before n equals 2, we have a0 is a half. And then a1 is now 1/2 plus 1/2 squared over 2, which is 5/8. And then a2 is 5/8 plus 5/8 squared over 2. And now, okay, it's getting quite complicated. So what is this? Okay, so it's some kind of sequence. I don't know. I'm not sure there's much to gain out of doing more examples, but yeah, I guess maybe some sort of straightforward observations that it increases, but not that fast. Okay. So any ideas where we can begin? So maybe one observation is if what we're trying to show is true, then this sequence is this sequence a0 through an. It's an increasing sequence that is bounded between 0 and 1. Um, and yeah, so let's make it, let's say something. So if the claim is true, then AK is always between 0 and 1. So one thing you can consider is 1 over AK is maybe I don't know, maybe it's a reasonable thing to consider. Um, and so I guess the first point is if you look at this guy, you can actually get some kind of reasonable, um, yeah, so you can get some reasonable idea of 1 over AK. So what do I mean? What I mean is that you can rewrite the recurrence as um, you can rewrite the recurrence as 1 over AK. No, that's not right. Uh, 1 over AK minus 1 equals 1 over AK plus um, AK minus 1 over AK times 1 over n. So I divided both sides by AK times AK minus 1. Okay. Um, so So was there any benefit to doing this? Yeah, so I think there is, right? Because now the point is what happens. This guy here, we already know our sequence is increasing, right? So this guy here is actually bounded by 1. So already this is less than or equal to um, 1 over AK plus 1 over N. So yeah, so does this give us anything now? Yeah, maybe I'll pause here for a bit. I think this gives us at least something, right? So any ideas? I claim that if this inequality that we have here, well, first of all, does it make sense where this inequality? Do you guys understand how we got this inequality?
Yeah.
Okay, so I claim that this should actually give you at least one part of this. So yeah, so what's the point here? So um, sorry, I didn't blue. You can rewrite this what we're trying to prove. It's the same as trying to prove that 1 over an is greater than 1 and less than 1 over 1 minus 1 over n. And the starting condition is the same as 1 over a0 equals 2. Right? And then what is this inequality telling us? It's saying that 1 over ak doesn't decrease by that much, right? So it's um, yeah, so 1 over ak is greater than 1 over ak minus 1 minus 1 over n. Um, and so in particular, 1 over an is greater than 1 over a0 minus n times 1 over n. Does that make sense? By like induction or something, which in this case is just 1. Does it make sense? So we get the right-hand side inequality. Does it make sense? What do we got, or how we got this?
I didn't get the last few steps.
Um, yeah. So I guess you understood up to here. Is this right?
Yes.
So the I guess okay. So this one is equivalent to this, and so what am I? I'm saying we have this, right? So this I've just rewritten the first inequality as this. And then what is the point? So we have a0. A0 is a half, so 1 over a0 is 2. Okay. And then we have like 1 over a1 is greater than 1 over a0 minus 1 over n. So that's 2 minus 1 over n. Um, and then a2, 1 over a2 is greater than 1 over a1 minus 1 over n.
Oh, okay. I think I
Which, yeah, and so on. And then you go so on, and so on. You get 1 over an is greater than 1 over a0 minus n times 1 over n, which is 1. Does it make sense now?
yes.
So, um, yeah, so I guess what I'm saying is I wanted you to think of this equation as saying that 1 over ak, we know it's a decreasing sequence, but it can't decrease that fast, right? There's a control on how fast it can decrease. Does it make sense now how I'm thinking of this inequality? So yeah, so I guess maybe I'll write it out. What I'm saying is, what does this inequality do? This controls oof, how fast. Well, maybe I'll write it bigger. Um, I'm saying what this inequality controls how fast 1 over ak decreases from 2. Does it make sense what I'm saying?
Yeah.
Um, okay, so we get half of the inequality for free, but now there's still left to do this side, right? To show maybe this, which is equivalent to this, right? Um, so any ideas how we can approach that? Maybe I'll say like so one side of the inequality, this side, right? This one came from just sort of some kind of trivial bound that this is at most 1. Um, so if we want to get this side, what we need to do is we need to give a better bound, and we have to give a lower bound for this. Does it make sense? So maybe I'll write what I'm saying. Um, So to show the other side that 1 over 1 minus 1 over n is greater than 1 over an, we will need a lower bound instead on ak minus 1 over ak. Does it make sense what I'm saying?
Yeah.
So let's be very explicit about this. Um, let's duplicate this. So to be completely explicit, the exact bound we need is so the exact bound that we need is yeah, so how can we set this up? Let's write it like this. Let's say just from here, right? We get 1 over ak minus 1 minus 1 over ak is equal to ak minus 1 over ak times 1 over n, which basically then tells us that, what does it tell us? It tells us 1 over an is equal to 1 over a0 plus sum from k equals 1. Maybe minus actually, minus sum k equals 1 to n, I think, k equals 1 to maybe n minus 1. No, k equals 1 to n of ak minus 1 over ak times 1 over n. Does that make sense? I'm rewriting this recurrence to write the last term in terms of the first term. And so what we want is okay, so what do we want? I think maybe we need more space, but okay, so let's start a new page. So okay, here's the point. 1 over an equals 1 over a0 minus the sum from k equals 1 to n, ak minus 1 over ak times 1 over n. So this is what we get from the recurrence. And now we want, so we want 1 over an is greater than rather less than n minus 1 over n, right? That's what this will be. No, that's not right. That's not quite right. So n over n minus 1. Yeah, I think that's what we want on this side. So so this is equivalent to n over n minus 1 being greater than 2 minus sum from k equals 1 to n, ak minus 1 over ak times 1 over n. um, which is then equivalent to saying sum k equals 1 to n, ak minus 1 over k is greater than n times 2 minus n over n minus 1, which is equal to hmm, n times n minus 2 over n minus 1. Okay, so that's the exact bound we want. Um, does it make sense what the purpose of this calculation was? Or is, I guess.
Yeah.
Yeah. Um, good, so this is what we want. So now, yeah, so let's just recall what the recurrence is. So the recurrence is this. So there are two ways of looking at it. We can look at it as ak equals ak minus 1 plus ak minus 1 squared over n, or we can look at it as 1 over ak minus 1 equals 1 over ak plus ak over ak minus 1 times 1 over n. And we want some kind of lower bound on ak minus 1 over ak. So any ideas how to do that? Yeah, so maybe looking at these two, how to lower bound ak minus 1 over ak. Sorry, this should say ak. Does the question make sense and like the relevance of this question?
Yeah.
Yes, maybe I'll give 5 minutes or so to think. There is something, basically the point is the next step is actually, you have to be very, very clever, but you can come up with it. You have to look at these equations or this recurrence, and you have to find some way to lower bound this ratio. Um, yeah, it's just some kind of clever observation. So any ideas?
Maybe we can multiply left-hand side of the first equation by right-hand side of the second equation and vice versa.
Yeah, so I guess the point is you want to somehow get AK and 1 over AK minus 1 together. So the idea, so what is the idea? Let's see. So I guess I can erase a lot of this. Maybe I can just say, uh, maybe I can erase this or something. Okay, so now we want, okay, so one idea is you can multiply these two, you can get AK over AK minus 1 equals this product, right? AK minus 1 plus AK minus 1 squared over n times 1 over AK plus AK over AK minus 1 times 1 over n. Okay, so is this a easier expression to work with? Let's think. So um,
I was thinking of doing the opposite.
the opposite.
First hand side with second right hand side and uh, first right hand side with second left hand side.
I see. So you want to do something like AK times 1 over AK plus AK over AK minus 1 times 1 over n is equal to 1 over AK minus 1 times AK minus 1 plus AK minus 1 squared over n, like this.
Yes.
Let's see. So maybe one thing I'll point out, this equation,
I think there's a mistake in the second equation.
there is. What have I?
Shouldn't it be a of k minus 1 over a of k?
Um, here?
Yes.
I see. Have I made a mistake? Let's see. So, uh, have I made a mistake in this whole thing? You're right. You're right. So maybe my entire, there's a problem here. Ah, yes, this is correct. Um, yes, you're right. Okay. Oh, okay. That's right. Yeah, yeah, but that's okay. Yeah, so right. So yeah, so this is okay because this is the term that we said is less than 1, right? So now we're trying to lower bound it. So this is consistent. This makes sense. Um, and now, yeah, so let's see. But maybe I guess all I really wanted to say is if you multiply it like this, right? Well, first of all, okay, you can just see they're both equal. Like yeah, you can see both sides are equal to um, 1 plus uh, AK minus 1 times 1 over n. Is that right? They're both equal. So this equation can't have any new information. Um, because like somehow like when you multiply them together, you've forgotten about the sequence, right? Like this is just a tautology. Do you see what I'm saying? And the reason is because, you know, secretly these two equations are the same. I just got one by dividing the other. So if you
Yeah.
so if you multiply it like this, you're actually recovering, you're losing all the information in the equations. Does it make sense what I'm saying?
Yeah.
So if you multiply it like this, that's okay because you're still remembering something. It's like you're squaring both sides and then dividing by something. But if you multiply like this, you're literally losing information. Okay, yeah, so let's try to think of something that could tell us about um, this bound. So actually, it's not a super sophisticated idea. Um, the point is you can take this guy and you can divide by AK minus 1. You can say this. So you can say, uh, and now, what was the whole? No, so yeah, why is this a reasonable perspective? Because, well, what are we trying to do? We're trying to lower bound this, which means we want to upper bound this. Okay. And now you have very tight control over this term because, well, maybe I'll write it, maybe I'll say in red. If the claim is true, if the claim is true, then this is actually between 1 and 1 plus 1 over n, right? Um, because remember, what are we trying to show? I mean, there's a lot of ways of phrasing it, but at the end of the day, what we're trying to show is that an is between 1 minus 1 over n and 1, right? And the sequence is increasing. So actually, um, yeah, so if the claim is true, there's a very tight control on this. But you actually don't even need the claim to be true if you want upper bound. Because remember, all we want is an upper bound. And to get an upper bound, this is less than or equal to, remember, the sequence is increasing, so this is less than or equal to 1 plus an over n. And this actually is less than 1 plus 1 over n because the previous part, right? The previous part actually um, was this, which is equivalent to this. Does it make sense? Does it make sense what I'm saying? So you can use the upper bound now to prove the lower bound. Right? Does it make sense what I'm saying? Right? So I'm claiming that we actually can get a lower bound for this by getting an upper bound for this, and the upper bound is exactly this. Does the argument make sense?
Yeah.
So let's complete the story. Abdullah, does it make sense? Okay, so let's just complete the argument. So what is the point here? Maybe I'll say this. So yeah, to finish the lower bound argument, we know okay, so we know this, and then that tells us what? That tells us ak minus 1 over ak is lower bounded by 1 over 1 plus 1 over n, which is equal to um, n over n plus 1. So the sum from k equals 1 to n, ak minus 1 over ak, is lower bounded by n squared over n plus 1, which then, okay, you can see this is bigger than n times n minus 2 over n minus 1. Yeah, and so that finishes the, the proof. Does that make sense? So it does the, did you,
Yeah.
yeah, okay, okay. Yeah, so any questions about this one? Yeah. Yeah, okay, so maybe we can do another one. So let's go over number 4. Yes, did you guys get a chance to think about number 4?
Yeah, I solved it.
Oh, you solved number 4. So then did you solve number 5 as well, or?
Um, moment. Um, I had already solved number 5 a few
Ah,
days before you sent us the homework.
okay, I see, I see.
I kept it somewhere.
I see, I see. And I see. And I said you said you saw number 7.
Yeah, I also
Di-
solved it once before.
okay, I see. And so number 6 had you seen before?
No, I
Okay.
couldn't solve it.
Okay. So maybe we can talk about number 6. So so what's the idea for number 6? Um, um, yeah, so what's the idea? Um, So if A0 is a natural number, actually, let's just start like this. So we have a sequence and it goes like this. So A0 is a natural number, and then AN plus 1, it looks like this. So it's AN over 5 if 5 divides AN, and otherwise it's the floor of AN times root 5. Yeah, so any ideas where we can start? And oh yeah, what is the problem? The problem is to show that uh, show that AN is eventually increasing. So what does that mean? It means you want to show eventually you're only in this case, right? So eventually the numbers are no longer divisible by 5. So any ideas how this can work? So actually, here's something that's very interesting, right? So, oh, there's a chat. Oh, okay, I see. Um, yeah, so there's something very interesting about this, which is if the statement is true, right? Like, yeah, okay, maybe I can say it like this. Here's a question. So let's assume that the problem is true. Then can you describe the numbers, the starting numbers, let's say, uh, uh, the starting numbers from which the sequence is increasing, right? Um, or maybe just like, can you just give like, is there some example like from where it's increasing? So what do I mean? Yeah, like can you give some example of a starting number from which the sequence from that point is increasing? So maybe you don't have to describe all of them, but like, is there just like, can you give some number? Does it make sense what I'm asking?
Yeah, but I couldn't find any numbers,
Um,
or at least I couldn't check if they were infinitely increased.
well, okay, so I guess we can start with like we can start with say maybe one example. So let's take okay, well there's one example that's obvious. There's maybe you can take 0, or maybe you don't count 0 as a natural number. Okay, but what's the next one after 0? What if we start with 1? So if you take 1, what happens? Hmm, so then we have what? Yeah, so I think maybe the first thing to really understand is what happens with A0 equals 1. So then we have A1 is the floor of root 5, which is 2. And then A2 is floor of 2 times root 5. which is 4, I think. A3 is um, which is what? Um, so this will be square root of this will be square root of 80, I think. So this will be 8. Is this right? Have I made a mistake? And A4 will be which is what? So now um, 320, which is I think 17 or something, maybe. Uh, Maybe it's 18. Maybe okay, I have to check that. I don't know. I can't do this in my head. Let's see. So yeah, so I think what happens is for here it's true, and so maybe I think what we should try to do is try to prove that it's true in this case. Yeah. So yeah, maybe here's the conjecture. If we start with 1, then it's true. So let's write it like this. So conjecture increasing if A0 equals 1. Okay. So basically what we need to show is that the sequence is never divisible by 5. So any ideas how this might work?
Um, I was thinking about that for every number, there's a unique A of n such that A of n time, or there's a unique natural such that the floor of uh, x times square root of 5 equals that number. So if we can somehow find the set of those numbers for uh, all numbers that are divisible by 5, um, we should be able to do it.
You're saying for all n there's a unique x such that maybe I'm not understanding the statement. For all n there is a unique x such that is this what you said?
Not for all n, but for all n that are achievable by this.
That are in the sequence you're saying?
Yeah.
I see. I see. And when you say unique x, you mean a unique integer x, is that right?
Yes.
Okay, I see. So that's so let's see. So why would this one be true? Um,
because if we increase or decrease x,
Yeah.
one would decrease by or increase by at least two.
Uh-huh. Good. Yeah. Okay. Yeah. So if something can happen, no, that's right. So that's right. So yeah, this is because root 5 is more than 2, right? So good. Good. So you're saying if a number appears in the sequence, you know what the previous term was. Okay. And then you're saying, and then what are you saying?
Yeah, we could use this fact.
I see. Good. Good. Um, and now you want to somehow say that what numbers can appear in the sequence, right? So, um,
Yeah, so I think if we can prove that there is x such that it doesn't appear in this set or in the set of five, and I'm not sure. It should.
mm,
Um, we can start with.
mm. Okay. So maybe so that maybe we can think of some ideas for 5 minutes. I'll be back in maybe in a couple minutes. Give me a moment. So any ideas how you can do this? Yeah, so remember, what we're trying to do is we're trying to show that this, at least for this one, it's always increasing. Mm. So let's see. Okay, maybe I'll say this. So I think this is a good problem to think about. So maybe I'll give you guys some time to think about this. So maybe next session I'll explain how to do this problem. Um, yeah, but okay.
Okay.
Yeah, because I think maybe it's good if you think about why this particular sequence and why it's increasing. Um, yeah, okay. Um, yeah, okay. Does that sound good?
Yeah.
Okay. Um, so for next time, yeah, so we'll go over this and then um, I'd also like to do some geometry. So I think what I'll do is let's see. You guys have Evan Chen's book, right?
Yeah.
Yeah.
So what I'll do is okay. So I'll send out some homework, but they will all be from basically the first two chapters. So there's 4 chapters in part 1. I want to do the first 2 chapters. So I'll send out some specific problems by maybe later today. So maybe, but it'll
Sure.
be by tomorrow. But they'll be from the first 2 chapters of Evan Chen's book. Um, yeah. So okay, so that'll be basically for next time. It'll be that and this problem here. But I guess what I want to do now before we break is, so did you guys get a chance to think about this question about 2 to the n ending in n?
Yeah. I proved it by induction.
Ah, okay, good. So do you want to review that at all, or is it okay?
I don't really need
Okay,
to.
okay. Abdullah, would you like to go over it at all, or
No, no.
okay, okay. All right, okay. So then I guess we can break for today. Yeah. So for Wednesday, it's yeah, we'll do this problem and then um yeah, we'll do some geometry. Okay. Let's